Hello students, today let us discuss the velocities of the two smooth spheres for the case of oblique impact. That means when their velocities are not along the line of centers. Now let me take these two spheres. One is of mass m1 and another one is of mass m2, where their velocities will not lie along the line of centers. The line of centers is this one, OO prime. So now let us discuss what will be their velocities after their impact. So now let us take u1 to be the velocity, m1 will be the mass of first sphere, and that is this one, and m2 is the mass of the second sphere. Now let us take u1 to be the velocity of first sphere before impact, making angle alpha 1 with respect to the line of centers. That means this is the direction of the velocity before impact for the first sphere, whose angle with respect to the line of centers is alpha 1. Let m2 or let u2 be the velocity of second sphere. This also before impact, making an angle alpha 2 with the line of centers. Now next, after impact they will have another velocity. So let me take v1 to be the velocity of first sphere after impact, making angle theta 1 with the line of centers. Next, let us take v2 to be the velocity of second sphere after impact, making angle theta 2, that is this one, making angle theta 2 with the line of centers, theta 2 with the line of centers. Now since the two spheres are smooth, so you have to note down this thing, that the impulsive action and reaction will take place only along the line of centers or parallel to the line of centers. So there will be no action and reaction perpendicular to the line of centers. Now you see that what will be the component velocity along the line of centers of this first sphere before impact? It will be u1 cos alpha 1, and perpendicular to the line of centers, the component velocity of this one will be u1 sine alpha 1. Similarly, after impact, I take v1 to be the velocity of the second sphere after impact, whose angle is theta 1 with respect to the line of centers. Now the component velocity of this v1 along the line of centers will be v1 cos theta 1, and perpendicular to it, it will be v1 sine theta 1. Similarly, for the second sphere, since u2 is velocity of the second sphere before impact, which makes an angle alpha 2 with respect to the line of centers, then the component velocity of this one along the line of centers will be u2 cos alpha 2, and perpendicular to the line of centers, it will be u2 sine alpha 2. Similarly, after the impact, the component velocity of this v2 will be v2 cos theta 2 along the line of centers, and perpendicular to it, it will be v2 sine theta 2. Now, since the two spheres are smooth, therefore the action and reaction will take place only along the line of centers. That means perpendicular to the line of centers, there will be no action or reaction. That means the component velocity will remain unchanged. That is, the component velocity of this one, first sphere before impact, that is perpendicular to it, will remain the same even after impact. Since you have to write now, since action and reaction takes place only along the line of centers, so the velocities, So the component velocities, you can write the component velocities perpendicular to the line of centers remain unchanged. So if they remain unchanged, it means that u1, this one, u1 sine alpha 1 will be the same as v1 sine theta 1. We can denote it as equation 1. And then this v2 sine theta 2 will be same as the component velocity perpendicular to the line of centers before impact. That is u2 sine alpha 2. Name it as equation 2. So now let us apply the two laws. That is, one is the conservation of linear momentum and another one is Newton's law of impact for this case also. Just like in the case of direct impact, for solving the problems related to the direct impact, we apply those two laws. That is Newton's law of impact and another one is the conservation of linear momentum. So now let us see by principle of conservation of momentum. So momentum after the total momentum after impact will be the same as the total momentum before impact. Now, what is a total momentum after impact? It is that is along the line of centers. So now we know that this is the component velocity of the first sphere after impact, which is along the line of centers, v1 cos theta 1, and v2 cos theta 2 is the component velocity of the second sphere after impact, that is along the line of centers. The mass of this one is m2 and the mass of this is m1. So the total momentum will be m1 v1 cos theta 1 plus m2 v2 cos theta 2. So this is the momentum after impact along the line of centers. And before impact, it is what we know that u1 cos alpha 1 is a component velocity of the first sphere before impact along the line of centers, and u2 cos alpha 2 is the component velocity of the second sphere before impact, that is along the line of centers. The mass of this is m2 and the mass of this is m1. So therefore the momentum will be m1 u1 cos alpha 1 plus m2 u2 cos alpha 2. So let us name this as equation 3. Now next let us apply this Newton experimental law. By Newton's experimental law, we have this one. The relative velocity of approach is equal to the ratio of the relative velocity of approach to the relative velocity of separation is equal to the constant E, which is called the coefficient of restitution. So in this case, what is the relative velocity of approach here? It will be that u1, remember that it should be along the line, the component velocities along the line of center. So it is u1 cos alpha 1 minus u2 cos alpha 2. And the relative velocity of separation along the line of centers is this one. For the first sphere, it is v1 cos theta 1, and for this one is v2 cos theta 2. So v2 cos theta 2 minus v1 cos theta 1 will give you the relative velocity of approach. So it will be v2 cos theta 2 minus v1 cos theta 1. This should be E times of the relative velocity of approach, that is u1 cos alpha 1 minus u2 cos alpha 2. So name this as equation 4. So now you multiply this equation 4. If you multiply this equation 4 by by m2 first, and then you solve it with this equation 3 that you got from the principle of conservation of linear momentum. So some terms will be cancelled, and then you'll see that because we are interested in finding what will be the component velocity of the first sphere after impact, which is that one along the line of impact. And also we need to find out what will be the velocity of the second sphere after impact, that is along the line of center. So we need to find out v1 cos theta 1, v2 cos theta 2 in terms of that u1 cos alpha 1 and u2 cos alpha 2. So now if you multiply this equation 4 by m2 and then subtract it from equation 3 and subtract it from 3, then you will have this equation. Some terms will be cancelled, so the remaining terms will be m1 plus m2 into v1 cos theta 1, because we want to cancel this v2 cos theta 2. So if you multiply this by m2, so you have m2 v2 cos theta 2, here m2 v2 cos theta 2. This is plus, this is plus. But if you subtract this 3 now from 4, after multiplying that 1, then you'll see that, subtract 4 after multiplying by m2 from equation 3, then you'll see that m2 v2 cos theta 2 and m2 v2 cos theta 2 will be cancelled. So this side you'll have m1 plus m2 v1 cos theta 1, which is equal to m1 minus e times m2 into u1 cos alpha 1 plus 1 plus e into m2 u2 cos alpha 2. So finally, what is v1 cos theta 1? It will be m1 minus em2 into u1 cos alpha 1 plus 1 plus e m2 u2 cos alpha 2. Whole thing divided by m1 plus m2. So this gives you the component velocity along the line of centers for the first sphere after impact. So what about the second sphere? What will be v2 cos theta 2 in terms of that alpha 2 and then u2 cos alpha 2. So for this one, you multiply equation 4 with m1 and then you add it with equation 3. Add it to 3. On adding this equation 4 after multiplying it by m1 to equation 3, then you'll see that m1 v1 cos theta 1 and that m1 v1 cos theta 1 will be cancelled. So you'll get m1 plus m2 v2 cos theta 2 is equal to 1 plus e m1 u1 cos alpha 1 plus m2 minus e m1 into u2 cos alpha 2. So this will give you v2 cos theta 2 equal to 1 plus e m1 u1 cos alpha 1 plus m2 minus e m1 into u2 cos alpha 2, whole thing divided by m1 plus m2. So using this Newton's experimental law, then principle of conservation of momentum, and also the condition that since the spheres are smooth or the ball are smooth, so their action and reaction will take place only along the line of centers. Therefore, their velocities after impact will be given by, for v1 cos theta 1 will be given by this formula, and for the second sphere that is after impact, which is along the line of centers, will be given by this formula. So hope it is clear. In the next discussion, in the next explanation, I'll give you how to use this principle of conservation of momentum and also the Newton's experimental law to solve the given problems for the case of oblique impact.